advising over 80 PhD and master's students. He revealed to us over lunch that he had 23 students at one time, all of which were funded, which is pretty astonishing to me. He retired from Kansas State University after his 27 years in March of 2014. He continues to hold a professor emeritus of agronomy at K-State. He also is a collaborator appointment here in the Department of Agronomy, working with a few labs on campus. Jody Edwards, Dr. Ying Yu, and Danny King's group. He's an author of over 150 publications and has served as an advisor on drone applications and agriculture to the United States National Research Council. He's conducted research in 14 countries and is among the pioneers in application of drone remote sensing technologies in agriculture. He has been cited in over 50 news articles and has spoken to over 15,000 conference attendees in the past 2 years on the related topic. So with no further ado, let's introduce Dr. Kevin Price.
Thank you. Can you hear me? Or I think it's working. Okay. Well, some of you heard me about a year and a half ago. I tried to put in some new material. Let me give you a quick introduction. First off, I'm going to introduce you to two types of drones and what they can and can't do, and show you some of the data we're collecting. There are a lot of people involved in this work besides myself. So these are people in our shop. Dr. Lynn Bryan in particular has been doing a lot of the analysis for us, and Dave Birchfield. Johnny does a lot of the programming and writes the algorithms for us. Mark is a graduate from Iowa State in computer science. Kirk DeMuth, Chief Operating Officer. Kirk and Daniel are some of the world's experts in drones. They tested the Predator. I've got pictures of them flying right next to the Predator. And then obviously we're working with these colleagues here. I wanted to thank them for the opportunity to work with them on some of the data collection. We're going to show some of the data. We haven't had a chance to analyze it all and tell you what it means, but we're going to show you what we're doing and where we're going with it. So our company has over 60 years, cumulative years in remote sensing. We're advanced digital image processors. We're trained in chemometrics, hyperspectral analysis, multispectral analysis. We do a little bit of work with thermal, but we cut our teeth on data processing and image analysis. 35 years in commercial aviation, 25 years in ag business and information technology, and 30 years cumulative in the UAV. Even though they've only been around a little while, we've got enough people who have been working in it as long as it's been around, so we know what we're doing with the UAVs as well. A little bit of my background. I started off as an ecologist at Brigham Young University, working on habitat community ecology. I then went up to the University of Utah and did my PhD in geography. And what's interesting is I ended up on the faculty in agronomy at K-State. That's a long story, but I loved it. It was a great opportunity. Notice one thing about this. Where I did my work, there was 3 dimensions to the environment. There was a third component. It's called topography. And you see the dark brown or blackish areas. That's called the shadow effect. And I'm going to show you a little bit about why that's important in a minute. But I struggled with that effect for years as an ecologist working in remote sensing. What you see, there's the sand dunes in White Sands, New Mexico. And you can see that the topographic effect is having a significant impact upon the spectral reflectance of sand. I don't think I could convince any of you that the sand here is different than the sand right there, but spectrally it's very different. And for years I worked with cosine correction techniques and all kinds of atmospheric adjustments to try to fix that. I finally found a solution to the problem. I moved to Kansas and got rid of the topographic effect. All right. So I taught at KU. I started there in 1989. I taught there for 19 years. I was the associate director of the Kansas Applied Remote Sensing Program. I had 50 remote sensors working with me there. And then the provost at K-State asked me to come over and give a talk. I thought, this is kind of weird. So I got over there, and they marched me into the conference room for the president of the university to give the talk. I thought, this is really weird. And I gave the talk, and the next day I got a call, and they offered me a job. So that was how I ended up at K-State. There's a little more to it than that. But anyway, there's 2 types of drones. There's fixed wing, like you see over here, and there's multi-rotor like you see over here, and most everyone flies multi-rotor because anyone can fly multi-rotor. You need to know what you're doing if you're going to fly this one. These right here, we say that the life expectancy of a drone is 1 year, all right? So if you're going to spend 30 grand on it, realize that it's going to last about 1 year on average. Now we make them last a lot longer, but most people don't. When I'm talking at a conference, I'll say, I'll be there in a conference with 800 people. I'll say, how many of you fly drones? And about 20 or 30 hands will go up. I say, how many of you have crashed your drone? And the same hands go up. It's like, did you pick it up in a garbage bag or did you walk away with it and just glue it back together? Most of them, I picked it up in a garbage bag. So they crash. So you need to be aware of that. If you're going to put a $40,000 sensor on it, just remember they crash, all right? And we've had them crash so hard they bounce 12 feet in the air. And the camera goes flying off. I was telling them at lunch, one of them went flying off up there, flew, did somersaults in the air, came down and landed in some bushes, and I thought, oh man, that's going to be broken. I walk over and I part the bushes and look in there, and I hear click, 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 click. And I pick it up and it's still shooting pictures. So I got a picture of me looking down at it in the bushes. So here's David. David flew a lot of the fields for the faculty here. And David just passed his written exam. He's going to be doing his actual practicum of flying the planes during the month of February, and he'll become a pilot so that he can come over and we can fly. We had to hire a pilot to come in and fly last year. But I'm going to show you what it looks like when you fly them. This has music, but we couldn't get the audio working, so it'll be the silent version. This is the multi-rotor. We call it a hexcopter. It's got 6 blades. Those blades are doing 17,000 RPM. They're carbon fiber. They're like butcher knives doing 17,000 RPM. So if you walk into them, just remember what it would be like to walk into a butcher knife doing 17,000 RPM, all right? They're not safe if you don't treat them right. People want to walk up and be right over them when they take up and fly, and I've seen them do some really crazy things, so you got to be careful. We're flying some winter wheat there at K-State. Jesse Poland, we're working on a grant from the NSF on high-throughput phenotyping, and we just got this started, and well, I'm here. So it was an interesting offer that pulled me out, and 7 of us left K-State and went to work to develop this company that the main group is just down the road here at Johnston. There's some color infrared imagery, a calibration panel of the winter wheat, and there's another calibration panel. We're showing you the kind of detail. You can see these multi-rotors are good for flying low and slow. You'll fly about 50 acres maximum a day if you're flying imagery that is map quality. If you're just getting up and looking obliquely around, you can get a lot more. But if you want map quality, you're going to have to fly, you're only going to get about 50 acres. All right, so you can see how high we're flying here. We train people on how to fly the drones, and these 2 agronomists came down from Canada last summer. In the spring, they are flying maniacs. They fly this fixed wing, and they go out. This is canola. They flew about 300 acres. They flew for 56 minutes in one flight with it and collected over 1,424 pictures in that approximate hour period. And then our job is to put all those pictures together and make them into one useful image. So I'll show you a little bit about that. We call that orthomosaicing. Yeah, I wish we had the music because it keeps you awake a little better. But this is our fixed wing. We designed this wing. We don't sell planes. I'm not here to sell you a plane. We built these for our dealers. They were out there selling these planes for way too much money. People are asking for 30 to 60 grand for a foam rubber plane. This is crazy. If you pay that much for a foam rubber plane, you deserve it, all right? This plane is designed to carry, it's got four bays in it. So you can carry multi-sensors, thermal scanners, multispectral scanners. It'll carry up to 6 pounds, so you can carry a full frame digital camera if you want on it. And it'll fly with the tailwind. We've had it up to 100 miles an hour, and the wings didn't come off, so it's holding up. We've crashed it from 200-300 feet in the air and picked it up and put it back in the air. The nice thing about the foam is that it's bumper car foam. So it's not beer cooler foam, it's the foam they put on your car bumpers. So you can get, you see they've launched that with a bungee. There's a rubber bungee that allows them to launch this. And some groups have you buy a metal catapult and they want to charge you $2,500 or more for the catapult. The bungee costs $30, you know, so it's a lot cheaper. But so this plane is really agile. The elevons at the back are made out of balsa wood, not foam, so it's very responsive. Just some little things that you should know about planes when you're flying them or looking at a drone if you're going to get one. The black tail fins, you can replace those by going to Hobby Lobby and buying the material if you want to. And this thing has got a lot of power. If you got a lot of power, it flies a lot less time. More power, it's more fun to fly, but it doesn't fly nearly as long. Hey, there's my gang. Come on in, gang. There's some seats right over here if you can't, over here. This is Lynn Bryan. Now I'm going to embarrass him a little bit. No, Dr. Bryan here, and Johnny Bryant, and David Birchfield. They are, they were all my grad students. They're getting rid of me as quickly as possible, and already have in many cases. But okay, so there's the drone. This is the Kirk. That's not Kirk. That's Daniel. Daniel is one of our drone pilot. That plane right there is a $250,000 drone, and obviously that is a multi-million-dollar drone. You look down in the corner, that's the wing of Kirk's plane as he's flying along, testing that and seeing how it's responding to different commands. To give you an idea, you don't get to do that unless you know what you're doing, right? At least you're not supposed to. All right, so let's talk about remote sensing. Just a quick course, 3 or 4 slides. I'm going to talk to you about an index. Probably most of you have heard of it. I'll ask to raise the hands maybe, but how many of you heard of the NDVI, the Normalized Difference Vegetation Index? All right, good. There's still some people in the room I can teach you this about. All right, so what we're doing with spectral data is we're measuring, when we're dealing with plants, we're measuring the way light interacts with the chlorophyll. And the more chlorophyll, the chloroplasts, the more the visible light in the red and the blue get absorbed for photosynthesis, and the more the canopy layers, the more the near-infrared reflects around. Think of it as a pinball machine with near-infrared. It goes into there, it hits the palisade cells, the spongy mesophyll cells, and it just bounces around like a pinball until, by random chance, half of it goes back out the top of the leaf, and the other half goes out the bottom of the leaf. And that's what it helps to magnify the amount of near-infrared. So if you get multiple layers or leaf layers, you keep having that same effect happening over and over again. And so it becomes kind of a magnifier for near-infrared. So I'm going to show you a soybean plant, kind of show you how this NDVI works. This is a soybean plant in the greenhouse. Part of it's a little bit sick, and this part over here is still a little bit healthy. And here that plant is in the blue, the green, the red, and the near-infrared. Notice that the dead leaves on the table look a lot like the live leaves on the plant. With near-infrared alone, it's difficult sometimes to tell the difference between live and dead. Notice that the healthy part of the plant is absorbing the energy, so it's dark. The sicker part of the plant is reflecting more of the light in the red and the near-infrared or the green, and so on. And so what we do is we look at the difference between the near-infrared, and so that's a minus sign, near-infrared minus red, or we can use blue or green, and then we have near-infrared plus red. And so what we're going to do is take near-infrared minus red divided by near-infrared plus red, and that normalizes it and gives you an NDVI. And now notice that the healthy part of the plant has higher values. The bright means the values are higher. The values usually range from 0 to 255, and the thicker part of the plant is darker. And so when we fly these aircraft over a field, we've got cameras in there that are recording the 3 bands to 4 bands, depends on what instrument we've got on there. They're recording for every pixel on the ground these values that we can convert so we can compute an NDVI for every pixel in the field. When we fly at 400 feet with the drone, we're getting about a 1-inch resolution. And we were flying over Jan Ming's and Ashi's, or Danny. Do you go by Danny? I didn't know Danny, but Danny. We're flying at 50 feet to 150 feet up. The pixels are about 7 millimeters to 17, 18 millimeters. So for every small area in that field, we've got pixel values or NDVI values. Notice we've colorized this now so that high NDVI is green and low NDVI is blue. Notice now we can tell the difference between the dead leaves and the healthy ones pretty well. All right, so I'm going to talk to you about some of the pitfalls or issues that you should be thinking about when you collect this kind of data, or if you collect it. We're going to talk about radial displacement, Y-orthomosaics, and bidirectional reflectance. This is showing that when you look down with a camera at an object, the only place that's true in its geography or geometry is straight below the camera. That's called the principal point. As you move away from the principal point out to the edge, you have more and more radial displacement. So the picture is leaning. Now notice that the trees look like they're leaning away from the middle. So as you get further away, you're looking more and more at the sides of the trees and less at the tops of the trees. So that creates a geometric error in your data set that has to be corrected if you're going to try to do true geometry. If you want to know if your GPS coordinate is in the right place, it has to be corrected. The other thing is that I'm pretending I've got a camera here. There's the lens. This is not working too. There we go. There's the lens. There's the film or the detector on the back of the camera, and here's two objects. Object 1, notice that object 1 and object 2 are in the same XY geographic location, but different Z location. So they're the same size, just at a different altitude or elevation. So object 1 is sitting over here and it's a different size than object 2, which is sitting over here and it's there. So two objects that are the same size, same geographic location, different elevations get placed in different spots in the picture. And this is the problem with cameras again. This is that kind of error. It's called displacement again. And so you have to have a way of fixing this in order to get the correct geometry in the image. Now the last one, and the way we do that is with an orthomosaic that builds a three-dimensional model and calculates the elevation of every pixel and then adjusts it and basically moves the pixel in and out to put it in its correct location on the picture. It's called an ortho. Ortho means true. You know, you've heard the Greek Orthodox Church. Obviously, the word orthodox was used to imply that they're the true church. And so when you have an ortho mosaic, it means that this mosaic is true. Is one way of thinking about it. Now, we also have what's called the bidirectional reflectance distribution function. Only NASA would come up with that one, BRDF. And with an acronym. NASA even has acronyms within acronyms. But this is PVC pipe. I've often joked that all research in the world would come to an end without PVC pipe. But that PVC, that's a 1/4 meter quadrat laying on some grasslands. And that is the same spot 9 times, only being viewed from 9 different viewing angles in that from the imagery. As we moved the drone around, we got pictures of the same plot 9 different times. So we went in and took samples out of those 9 plots and plotted them. And there's your brightness values in the green, the red, and the near infrared. You see what viewing angle does to your data? It makes it all variable. So you have to correct for bidirectional reflectance. Or an NDVI will help normalize it some. The normalization is kind of working here. Not perfect, but what you have to do is get lots and lots of overlap between the images. We do about 70% overlap. So we have to fly a lot longer to get the overlap so that we can then use the different viewing angles to correct every orthomosaic for its proper geometry and viewing angle. All right, here's David, the backside of David. I'm going to show you some of the data that he flew over winter wheat. We showed you the video. Here's the winter wheat plots. Everyone comes out to see the drone. After a while, they'll get bored with them, but for right now, they're still novel. Well, there's the plots. Jesse hates it when I show this because you can tell his GPS wasn't working right on that planter. He said that picture showed up on the cover of, I think, the Agronomy Journal or something like that, to even make it worse. But anyway, this is some low elevation when the winter wheat is senesced pretty heavily. And so that you know you're not the only ones that have weeds in your field, there's some weeds growing there. And so weeds, and then there's the winter wheat plots. And if you want real detail, David did fly a little low on this one, but you can count seed heads if you want, just about from this kind of data. Here David laid some plots on each of the, some sampling plots on them, and extracted the data, and then he computed, in this case, the average NDVI value using the green band, and then showed the variation in the mean NDVI for the plots, to show you the variation that's going on by the way those plots are reflecting. A plant that is more senescent is going to have a lower NDVI than one that's still photosynthetically active. The other thing that he did was calculate, he had over 63,000 samples within the plot, and he calculated the standard deviation of all those 63,000 samples, and then plotted that to show the variation, show higher variation in red. You notice there's not a lot of difference here, but it does pick up some interesting patterns. And what we'd hope is that those would correlate with some genetic interest, things that are interesting from a genetic standpoint or from a phenological standpoint. This is a shot I took with a color infrared camera on the ground. That's soybean, and obviously there's trees. What can you see? Let's look at some of the data. This is some of the shots that we shot. Jianming, the picture I had of you was completely blurry, so I didn't fault. It was my fault. So Jianming, we took pictures. What we got is obviously we've got a couple of faculty members out here. We've got some grad students, people getting sunburned tonsils watching drones. But the thing that I also want to point out, sometimes people are saying, I don't know, it's against the law to use these drones. We want you to know we're flying very, very legally. We have what's called the 333 exemption. We can fly anywhere that's not restricted airspace in the United States legally. There's I just pulled off a little bit of the form. I can give you the whole letter, but down here it tells all the things we can do. This is from the FAA, and we are fully authorized to fly as a legal organization. Plus we have liability insurance, so in case we mess up, okay? Hopefully, I hope we have enough. I don't know. I asked them how much. They said, the person I asked said, I don't have to go check. Never mind, I don't need it right now. So, also, every time that David flew here, he had to fill out this. This is an FAA NOTAM. And to fly, you have to be, now the rules are you have to be a pilot. And so you have to have a pilot's license. So David is going to be going, as I said, and here David, he flew quite a while with gliders, braver than I am. I'd always be afraid I'd get out somewhere and couldn't make it back. But anyway, David will be down in Burlington, Colorado, taking his flying tests the month of February. And he's taken the exam there at Ankeny and passed it in flying colors. So you have to be able to fill this out, tell the FAA where you're going to be flying and when. And you have to have a pilot. And so we didn't have a pilot here. All our pilots from Colorado. We brought one of them all the way up from Colorado the first time we flew. But this is a pilot from this area. He had his daughter. I'm calling her the pilot in training. But she wanted to see what he could see on that. This is so that you can monitor the telemetry of the plane while it's flying, to make sure that it's not flying outside the area that it's supposed to be flying. If it flies out of that area, you've got to hit a return to home switch and hope it works and bring it back. And believe me, I see it happen. I don't know if it ever happened to you last summer, did it, David? All right, getting better. But when we were first doing this 3 or 4 years ago, it was not uncommon for our planes to go renegade on us. Here's the plane, the multi-rotor we flew. There's a video. Daniel's taking it easy on this one. Flying a little corn here at the agronomy farm. Notice the cloud cover. We don't normally fly, especially in that kind of cloud cover, but because we brought Daniel all the way up from Burlington, and he was waiting until there was no cloud cover over the field and then going out and flying it. So in between the clouds. It's not ideal. In this case, we had to do it or get no data at all. And so that's just showing it flying off into the west. I've had it where it just kept going and kept going and kept going, and I've had to crash them, bring them down in a hurry, and I landed one in a cornfield, and all I saw was corn stalks shooting 10 feet in the air when it hit. It was just mowing them down everywhere. I never told the guy whose field it was what I'd done. It was only a half a row, but anyway, I'm kind of kidding. All right, so this is one of, I think this is one of Jan Ming's fields. Give you an idea how many pictures we're taking, 640 images between 8 and 10 megapixels, megabytes per image. This particular file was about 5.6 gigabytes of data in one flight. So we're really pushing a lot of data. And this one here is showing the same field, and with our software that we've developed as part of our portal, you can click on any of those dots and it'll pull up this little window, and you click up there on the image and it'll pull the original image up and let you see the full resolution image if you want to look at it. And here we flew this area 3 times, so there's the 3 data sets with the different products that were produced, and I won't go through those, but it's all right there at fingertip. You can click on it, bring up your data. We turn the data around in less than 24 hours. We have it back to you and ready for you to download so you can start working with it. Here's a single image over some corn. Probably some of you are familiar with that area, a little shed and so on. And you're looking at it kind of in the earlier growth stages here, a little later growth stages there. Here's some soybean. I want to show you that it's not just pictures. These are plots. I've taken and just pulled up a sample here, here, and here. And here's the pilot looking up. And when we pull that into the software and pull the data out, there's the distribution of values for that plot. You can see how there's more variation in that plot with bare soil. So you got a lot different histogram for that one versus this one here, which is right here in purple. So they've got different distributions, and it was a quick and dirty sample just to demonstrate the point. If I were being very meticulous, I would sample just on a certain portion of that canopy to make sure I wasn't getting differences in illumination angles from the sun. Here's 3 fields. This is July the 13th, August the 6th, September the 1st, showing the differences in phenological development stages. And then we put down calibration panels, and this is showing a panel that we've painted with just regular house paint, but it's a color that we found that works really well. And there's the panels from the Imagery, and these are X's are ground control points, so we can georegister the images to each other for different dates. And then to see if the normalization process worked, when we took the values off the panel for the 13th, the 6th, and 1st of July, August, and September, the original value on the panel, the average for the first date was 139. In August it was 131, and in September it was 135. So we normalized the data with the panel, went back, the panel was 99, 99, and 99. So we have normalized for sun angle. That helps remove some of the variation due to the time of day that you fly. What it doesn't take out is the fact that different sun angles will create different shadow patterns within your canopy. And I showed you the topographic effect. I didn't get away with it completely because there's still a topographic effect at the micro level. What we're figuring out to do, though, is how to use those shadows to characterize differences in canopy geometry. So here's some examples of just a small sample of one of the fields and just one of the corners of the field. And here are the polygons that Lynn's putting those polygons in. Lynn, are you still blind? This is very tedious work. We haven't figured out how to automate it yet. It's a lot trickier than you may think. So we're laying those excuse me, polygons in there. That I better get some water. So we're laying these polygons in here. Whoa, what happened? And I think my voice will come back. I don't know what happened. It just ran away somewhere. Okay, so here it comes. Okay, so here we're looking at all those plots, and Lynn classified them according to the brightness value from a band called the red edge. It's right on the near infrared red region. And so she's shown the green ones have a higher brightness value in the red edge, and the red ones have lower. So we're classifying the field into different categories of red edge. And here's using the green band doing the same thing. If you look closely, there is a little bit difference between them. There's a lot of similarities. And then she did a standard deviation on it, because we've got thousands of pixels. We can run a standard deviation. So we're looking for the areas that plots. There's a plot that has a lot of variability in it. And so we're looking at variability of the plots and then classifying them into different variability and this was the green band and this was the red edge band on standard deviations. This is some earlier work we did in 2014 with Jan Ming on sorghum, and we're showing that you can pick up the bags that they're using to I think you're covering tassels probably or seed heads or something here. And so that's the level of detail you can see in the imagery. We went in and classified the image into the height of the canopy. And so here is the green is the top part of the canopy, and the yellowish is more the middle part, the leaves that are in the middle, and the blue are the lower leaves that are down closer to the bottom. And so we wanted to look to see how the area by canopy level changes with the different genetic types. So here we've got a zoom in showing you the canopy being classified according to the height of the leaves in the canopy, and then going in along a track, pulling the plots out along the track and classifying all those plots, and then building a graph showing the amount of area in lower leaves versus upper leaves, with the bars showing, for example, the first one has a lot more lower leaf showing in than the upper leaf. That might be one you want to select for if you're trying to get more light down into the canopy and you want a more erect canopy with the top leaves. Here's a zoom in showing you an example of 4 of them. So this is the classification, and that's the color infrared for that classification. And this graph up here goes with this one here. So that's showing us that in this image, it's about just a little less than 40% of it is lower leaf, and about 25% of it is upper leaf. And here we've got more lower leaf showing through than upper leaf. And these two, we've got just the opposite. We've got the upper leaves are shadowing the lower leaves. So what we've got is we would probably, if I were picking for phenotypes, I might say I want those two. I want plot number 24 and 41. I don't want 24 and 47. And here is using what we call a landscape ecology metric. We're bringing in landscape ecology to look at contagion. And that's the amount of connectivity. If we're looking at the leaves in there, trying to determine what percent of the top leaves, you can notice that there's less green in these than there is on that one, and so on. This means that there's more leaf area at the top of the plant than on the lower part of the plant. So here again, the example 23 and 24, it has less contagion, there's less connectivity, and here's more connectivity. So if you're an ecologist working on wildlife, you want to know if there's ways for an animal to get from here to here by having things connecting. Well, in genetics, we're using it as a method for determining whether or not there's more area at the top of the plant than there is at the bottom, and so we would more likely select for these two and select against those two, as just an example. If you want to count seed heads, the little blue dots are the seed heads. Okay, now we move from basic statistics, we call them summary statistics, into what I was just showing you is some of what we call also geospatial analysis. Remember, I've got a PhD in geography. So as a geographer, I had to learn about spatial autocorrelation and aerial correspondence analysis and different things that we use in geographic information systems. So I'm going to show you some examples from work we did on a threatened and endangered prairie chicken. And hopefully you'll make the connection on how this could be used in plant breeding. Here is the truck on the ground. The little white panels are panels that were put out by the biologists, and then they took and put their sample plot exactly halfway between the panels. So we knew we needed to sample right there and there and there and so, and there were hundreds of these out there. There weren't just these few. But we'll just pull up a few as an example. Oh, by the way, you can see that's cattle. If you're wondering what the black things are, those are cows around a water trough right there. And these are shrubs, and differences in the light means more bare soil, less bare soil, so on. All right. So here is plot 45 and plot 58. And sometimes they put the plots so close together that the circles we did the analysis on coalesced. But the point we want to make is if we did an analysis of the variability as a function of distance from a point, we start here and we want to move in multiple directions away from the center, how rapidly is the brightness values changing as a function of distance from the center? And so this graph is showing that. This is a variogram. And what it's showing is if I'm 1 pixel away, how similar is the pixel? If I'm 2 pixels, 3 pixels, out 75 pixels, which is about 4 meters away in this particular case. So we're seeing that if the environment is extremely homogeneous, it doesn't change much as you move away from the center. If it's more heterogeneous, it changes more rapidly. So this one's more homogeneous, this one's more heterogeneous. And you can tweak this to be more sensitive or less sensitive depending on what you're trying to accomplish. So here's plot 49, 47, or no, 48, 47, 46. And here they are plotted. Now if I'm a prairie chicken, where do I want to build a nest? Can we predict where the prairie chicken is most likely going to select to put its nesting site? If I'm a plant breeder, do the canopy types that are more heterogeneous, is that more desirable or less heterogeneous? I don't know the answer. I would like to ask that question or have you be able to ask that question. But here is the plot 49. You see that one going up? That's telling us it's more heterogeneous. And then it starts to come back down and become more like it was over here. So it could be a systematic pattern that's in the data. So plot 49 is this one right here. And remember that it's picking up subtle differences in the brightness values that we may not see in the coloration of these maps. We can only detect about 8 to 16 shades of gray. The cameras we're using can detect over 16,000 intensities of energy. So what we see standing there may not be the same thing. And you're talking about your ultraviolet for sunflowers. What you see standing there often is not what organisms or animals are seeing either. Now we took a random sample of points around an area, and then we took the samples of known nesting sites to see if there was a statistical difference between the sites the birds selected for versus random sites. And there was. This one up here is where the random values ended up being. And this one down here is the site that was selected for by the birds more often. It's not a perfect match, but if you're trying to play the game of probability, it's telling us that a site that's more like this is more likely to be selected for than one that's like that one. Danny, I hope I'm not showing something you don't want me to show. If I do, you can kick my behind afterwards, all right? Okay. We are working on some soybean, and we're taking samples here. Here's a part of the field. We've taken a lot of samples, and what we did is just took some samples throughout the field here to do some analysis. We didn't want to try to do all the analysis on this. It was just a lot more work than we were doing this just to test it, okay? So the thing that we did was use cluster analysis. And with the cluster analysis, we took the statistics from all the plots and determined where the plots were clustering, which ones had similar spectral characteristics. And then we tested those clusters. We looked at 4 clusters, and we tested them to see if they were statistically different from one another. And we looked at them in terms of the minimum value, the mean, here's the max, and how they changed over time. and when is the optimal time for detecting one canopy type from another. And so that's what this is showing. I know it's a lot of data to look at. I'm just trying to get across the main ideas here, and rather than sit and drill you through every little point on there. Here's some corn plots showing on July the 14th. The corn was was only up about knee high. And so we took 4 little samples and we zoomed in on it, and there's what the sample plot looks like for plot number 1. In other words, this is the little sliver taken out of that one. And you can see the red, the differences in the corn leaves. And we're not sampling the whole plot because they're not very wide yet. They're pretty narrow because they're young. Next time we sample it, August the 6th, it's wider, so we can use a little wider sample. And there's plot 1, 14, 42, and 44, and you can see these differences in the canopy. Here it is again on October the 6th. We did one more of a flight, but I just put 3 of them in. So here now they've got the bags on them, but we can see you can see this one versus this one and this one and this one. So what we do is we go in and we start analyzing the spatial arrangement of the leaves. We want to look at inclination angles and how much of the leaf is being illuminated by sun at any time over the day and through the growing season, or where you can go with this. And some statistics to show, in this case, the best time for separating them, looking at the mean red edge, which looks like August the 6th. Here we see that plot number 1 was quite different than the other throughout the growing season. Whether that's meaningful, I don't know. That's where the data collected in the field starts telling us that. 3-dimensional models. The reason you see in 3D is because one eye is seeing it from one angle and the other eye is seeing it from another angle. We can use the camera as 2 eyeballs. If you take a picture and then you move a little further and take another picture, it's like 2 eyeballs. It's just that they didn't see it at the same time. So you calculate parallax in your data set and you can build a 3D model. The accuracy of the model is plus or minus 1 pixel size. The pixel here was 7 millimeters, so the accuracy should be within plus or minus 7 millimeters of accuracy on height of the plant. How many of us can go out and measure it in the field at that level of accuracy? I can't. I know my graduate students can if it's a hot sunny day. And all right, so here's a profile going across that field. The edge rows, then the main crop and genetic breeding plots going across, and then coming back down to this lower area right here, and then off onto the road right there. We think it has a lot of promise. You can't get, you have to resample the data and make it coarser. So if you've got 17 millimeter data, by the time you resample to be able to calculate altitude, it may be, instead of 7 millimeters, it may be about that big around, because you've got to get enough slope to build what they call triangular irregular networks to be able to calculate it. Jody's, we've flown some of Jody's fields. In fact, we flew a lot of Jody's fields. Jody, are you here? All right, good. Jody, pipe in if you, maybe there's some stuff here you'd like to say when I get to one of these, but what we're showing here is the differences in phenology. This was flown with the Cessna, so we're now at about 2-inch resolution instead of 7 millimeters or 1 centimeter. And here is the plots, and you can see the differences in the genetics in terms of when the plants are browning down. And here is a field we flew this year, and you can see the variation in the field. This is a single image. So we mosaic multiple images together, and here's an orthomosaic. This one, the date on this was September, I think the 3rd. I can't remember exact date. This is the color infrared, and so you can see the variation going all over in this field. And this is an enhancement. And Jody, you want me to hand you the pointer, or you want to say anything about this? All right, well, we can't see it nearly as well as you can see it on his monitor, but you can tell differences in plant density. Jody was able to discover areas in the field that he wants to change the way he's using it because of environmental conditions that are affecting the outcome of his plot studies and so on. There's all kinds of variation in there that we're picking up, and Jody can tell you more about this one than I can. This is the NDVI map, colorized, so that lower NDVI. So more advanced stages of senescence, less advanced stages of senescence, and so on. All right, last thing. Okay, I'm going to go quick on this. I'm going to switch gears on you. We're also doing stuff with satellite imagery. We're looking at the Earth from outer space. And I started this work 15 years ago with NASA funding and started working on developing methods for forecasting yields on crops, and was hired by the USDA Foreign Ag Service to come in and train them in Washington on how to use the technology to predict yields. I'm not going to claim that the yields we're making right now are perfect yet. We've still got a lot of work to do, but we're pretty excited about it so far. This is an NDVI map for the end of July of this last year. And the brown areas are lower NDVI and the green are high NDVI. Now, this is compared to the average for the last 15 years. So anything that's green means it's greener than it normally is in that area at that time of year. And anything that's this color means that it hasn't changed. Well, the desert's not going to change very much. And any areas that are brown means that it's drought probably, or something that's causing it to be less green than it normally is. This one is compared to the previous week. So any areas that are brown are less green this week than they were the previous week. And any areas that are greener than they were the previous week. So this is getting into rate of green up. And what we're looking at is, when does the plant green up? How quickly does it green up? When does it reach maximum greenness? How quickly did it go into senescence? To look at the phenological development stages this is a 15.4 acre resolution. This is not 1 millimeter or 1 centimeter. It's 15.4 acre resolution, or 5.6 or 6.5 hectares, I believe it is. This one is compared to last year. So anything that's green is greener this year at the end of July than it was last year at the end of July. So let's zoom into Iowa a little more. We can zoom all the way into the county level. And with the way it's being developed, Johnny's been working on this. You can pull up the entire continental, most of North America, and move your cursor around, and the computer will start building graphs for you, showing statistics. We'll show you in a minute. The NDVI, here's compared to last year, compared to the previous week, compared to that was a 15-year average this is compared to last year. So these areas in Iowa are not as green as they were last year, is what that's telling us. And other areas are greener. And finally, let's get into, I'm going to be brave here and show you some of the modeling we're doing. Again, don't throw rocks at us yet, but this is trend. If we plotted for soybean, how many bushel per acre we harvested for the state of Iowa every year going back to what year is that? I can't read it very well. Oh, wait a minute, right here. 1985. So going back to 1985, plotting the bushels per acre. How many, I don't know what the soybean was this year. Anyone hear what the corn was this year? 192. The highest in the past was 181. We broke it by 11 bushel per acre. We're still kind of stunned by that one. But this is showing the improvement in yields due to genetics and farm management. And so anyone can predict the trend, can take that trend line and predict what the yields would be. But if you predicted it in 2003, you would have predicted it here and it would have been clear down here. So it's not a really good model. But if you can't beat that model, then get out of the business, right? If you can't beat trend. So here we compare the USDA's early estimate of yield and trend, and this is our predictions of yield, and the bottom line is USDA's final estimate at the end of the growing season. So this is what the USDA said it was for each of those years. This is what we predicted it was 4 months ahead of the USDA. Okay? And this is what the USDA's in-season estimates were for each of those years. Here for soybean, we found that We could be within 2.2% of the USDA's final estimate on July the 15th, about that time, but we were pretty close earlier too. And here is the correlation of our model. We, for each year, or for over the growing season, for all the years we looked at, we find that on July the 29th, we can explain about 96% of the variation in the yield for the state of Iowa. And here is the curve I told you about, building vegetation phenology metrics. You can click and the graph will come up for the whole state, for the crop reporting district, or the ag statistic district now they call them, and for the county, telling you, showing you the dotted line is the average for the last 15 years. The yellow line is what the NDVI value was last year, and the green line is what it is this year for soybean. And it's showing that, if I go to the next slide, it's showing that during this would be about when it's planted. During this period, the plants are a little bit higher during the vegetative stage of development. It's a little higher than average. But as it moves into the R1, starts blooming, and starts moving into R2 a little bit further, and then goes into the pod filling stages, we can see that this year it was well above normal. So we would forecast a better than normal yield for soybean. But a year like this year with the extremes that we hit, it's tough to be modeling in a year like these. If you can do it, you're really, really good. So here is 2004. This was trend. This is our model. We started predicting yield on soybean on about the beginning of April, middle of March. Predicting it, we get better and better as we come across. The black line is what USDA's final estimate is for 2004. This is 2014. So there's trend. We weren't beating trend, but trend was awfully good because it was within 0.5% of the final in 2014, and we were within 1% of the final. And this is how the model was predicting, and it looks like it's awfully variable until you look at the y-axis and realize it's within about 3%. Am I getting this right, Johnny? All right. Thank you. Are there any questions? I'll give you that, and I'll use 2 hands here.
All right, are there any questions for Dr. Price? Yes.
No hard ones.
Okay. So you say that you couldn't really automate to differentiate plots on the pictures yet. Does that mean if you take a picture, you always have to send someone to actually circle out the plots that you want to measure?
Do you have to send it to some, do you mean do they have to send it to us?
Yeah, or just have a person to do
No, there's lots of people. Oh. No. People who are processing their own data. The question is, I think the question you should be asking is, are you comfortable in doing image processing? There may be a lot of things that you may not know that would cause you to make mistakes with it and not get the data quite right, because you have to do a lot of normalization and so on. I'm not trying to scare you, but I'm just saying you need to be aware of it. Maria?
We're doing it on the mic so it can be recorded for the
Okay.
podcast. Sorry about that.
Okay. Thank you, Dr. Price. I wanted to ask you, for these differences in the canopy that you show, did you consider other parameters like plant density?
Yeah, I gotta wait. Did we consider plant density? Not on this, but we've done work on plant density, and we find some pretty good relationship. Now, Jody's field certainly was picking up some differences in plant density, according to what he was telling me today in his office. But we haven't tested it in these fields yet here at Iowa State. But we've had farmers from Canada and other places that have sent us data in, and we've looked at the relationship. And, you know, quite often they want to know exactly how many plants there are. We're not sure we can tell you exactly how many plants, but we can certainly tell you, give a prediction that may be close enough to be still very useful. And it depends on the plant, too.
Other questions?
Sorry, Dr. Price. This is coming back to data processing. So you said 5.6 gigs. That's what you're pulling down when you do a run over a field. So no one's drawing or demarcations on 5.6 gigs of photos, right?
No, we build them into an orthomosaic. And the orthomosaic may be, it depends on the area. We've had some orthomosaics. Full resolution would be close to a gig. But if we resample it to a coarser resolution, then we can get them down to a smaller size. It's easier to handle on a computer. But we've got the computing power to handle it. We can process over 1 million acres a day. So we are less worried about that than I was when I was at K-State. I told over lunch that we flew an area when I was at K-State. I had the fastest computer I could buy, desktop, and we processed the data for 8 days and the computer crashed. And so we started it again and went for 8.5 days, and we finally got it. And we put that same data set on our computer and had it done in about 15 minutes. So you got to have a lot of computing power. About $1 million worth of computing power would do it. And some programmers are really, really good at optimizing too. Yeah, it's just a lot of data, no matter where you look at it.
Other questions?
I'm wondering whether you put the GPS in your drawing, because I'm thinking about the repeatability. You already show is very good, but I'm wondering is like a sunny day, raining day, whatever day on ahead. So if you have a GPS, we know some company put the GPS in their planter, then you use the coordinator that consistent with the coordinator from the planter, then you know where the plot exact is. Then since GPS is there, you know where how much height, and where you start to take the points just above or some angle. Since the GPS can tell you, you can automatically say, okay, this is the point, I will take a picture just below, then repeatability may be better. And also easy to differentiate where the plot, since you have the coordinate.
A real good question. That was a real good question. So what you're trying to do is maintain the viewing angle of the plant, you're saying, by having GPS over it. The way we do that is that in the orthomosaicing process, our computer selects for the images that are most nadir over the plot when they're building the orthomosaic. And so, and then the brightness coming in from the sun can change if there's wispy clouds that go over and so on. So there's lots of variables, but I'm not going to concede that it's a confounding problem that discourages me, because I've gone out and done enough field work and know what it's like to do field work and know how many confounding problems there are there too. But yes, if you had the GPS, you can get straight over, but you'd almost have to put it over hundreds and hundreds of points. It's a lot faster to just fly the whole field and get lots of overlap and let the computer pick the images that are straight over as much as possible. But that's a good idea. Yeah.
Yeah, I have a question about the forecast. I really like this predictions was pretty close. So the first part of the question was at national level, Iowa State, the forecast?
The forecast?
Yeah.
It's for the whole state of Iowa, yeah, for Iowa.
Have you tried to make a higher resolution for a specific field?
Yeah, we can do down to the county level.
More for a field level?
If you gave us yield data for an area, we could do it then more, but the
Okay.
yield data we have is at the county level. So what's constraining us is not our data, it's the level at which we have yield data.
Okay.
Okay.
Thanks.
Have you tried the hyperspectral imaging? How's that work relative to NDVI?
You're not going to like my answer. Yeah, I've been working in hyperspectral for 25 years. The data I've processed is 2,151 bands on the spectral radiometer. We've gone out and collected data on soybean plants for 10,000 plots with Bill Shapaw, and taken hyperspectral data from a spectral radiometer, not imagery, and I have done image analysis too with hyperspectral. And what I have been looking for the magic bullet for 25 years, all right? I haven't found it. And as I was telling him at lunch, the people who think they found it usually found it in the laboratory, and then they took it out in the real world and found out that the noise in the data was so much that it completely overwhelmed these important little absorption features in the hyperspectral data. And so when we do partial least squares regression analysis on the hyperspectral or principal components, we end up with usually three or four components, and the first 2 or 3 explain most of the variation in the 2,000 bands. And so we can boil it down. We start looking, and we find a good visible band, usually in the red region or in the green, and one in the near infrared. There's a lot of excitement about red edge, and our work is showing that the red edge is not as good as I would not take it. I would take a near infrared band over a red edge band, because the near infrared, the red edge is right on the transition between red and near infrared. So you've got the visible light that's being absorbed by the plant and the near infrared that's being reflected, and they're kind of in a tug-of-war. And so they almost cancel each other out, is what we found. And our poorest correlations come in the red edge region. I'm going to get beat up yet. Also on a drone, I would never dare fly a hyperspectral scanner. Remember, the life expectancy of a drone is not a year. I'm not going to put a $40,000 to $100,000 instrument on a crashing aircraft. Yes, Chris.
So I was noticing on your website, you talk about a dealership network that you guys have, and that's more oriented towards ag products in the field. And I'm wondering, from your experience working with your network, what are your products that are most commonly asked for, or which are the ones that services seem to request the most often?
Do you want to answer that one for me?
I can give it a shot.
Okay.
It can be really variable depending on the region. There's a lot of interest among some of the crop scouts in just the relative health NDVI of the field, looking for issues in the field, and just to be smarter scouts, to find the issues and to know where to go look, as opposed to just go walking blindly through the field. So that's one that comes up. Another one that comes up a lot are looking for issues with equipment. So anything looking at density issues caused by compaction. And then we've got actually really recently, of course, mostly because it's not really nothing's growing, 3D products, so topo maps, elevation maps showing the elevation of some in the field and then some in the non-ag industry. But in the ag industry, there's a big interest in whether you can find tile lines and damage in tile lines and stuff like that.
Johnny made me think of something that I think you'll find interesting. Down in Guatemala, we have a big sugarcane growing company that we're working with, and they found from looking at our imagery, being able to see the NDVI, they were able to determine that their sprayer was miscalibrated, and because it was spraying too much on one side, they killed the sugarcane. Instead of browning it down, they were killing it, and there was these interesting stripes, and when we overlaid, or they overlaid, their GPS coordinates of their sprayer, their air tractor, on top of their data, they could see that it was perfectly correlated with the spray patterns. And then they were able to go in and set up cards throughout the field and look at the spray droplets and knew how big the droplets were and the density of the droplets, and were able to detect that they were killing the sugarcane. Now they've got a field that with stripes going through it where they've got to replant, and everything will be at different age stages and so on. It's a real mess. But they didn't even know it was happening until they saw the imagery. So.
All right, well, in an interest of time, I know a couple people might have kids to pick up from daycare and get home. Please be careful. It looks like the roads are now snow covered since you got here. But if you'd like to ask additional questions, feel free to come on up. And thank you all for coming. And let's give Dr. Price one last round of thank you.